We're gonna work on some next. Oh, I mean, I'll get off. No, Stefan's there. So I think we could be either before or after. Let's see what you mean. Before or after. I'll probably start. Can't do two things in one night, dude. You can only do one. This is nice. Some of them are probably
Yeah, perhaps a few announcements for you guys. So one thing we've realized is that the TMs, for some of the students, the outputs of your homework assignment are not shown. And that makes it very difficult for us to grade. And you know, we can't run them because it takes time for the output to actually show. So imagine we have like say 10 or 5 students and we have to run it. It might take some time. So what we are going to do is, if your outputs are not showing, we give you a 0 for that. Because it's your duty to run them and show us the output. It's not our work to run your code once again and then grade it. So this is just an information for you guys. Okay.
So from next time onwards, please make sure that your submission is with the output of it. It's not that you did it and just didn't consider the output to be part of it. Please make sure that.
Okay, so if you run your code through it and you download it, should it download with the output, or you have to do it special to download the output?
No, so output should be a part of a Jupyter notebook.
Okay, I think so. I just didn't know.
What's that?
Yeah, I would think so. I just didn't know if that's how it's in there.
Okay, guys. So let's start today. Today we will just look into the different techniques which we could use to visualize the intermediate layers of the deep neural network. So this is also this will also help us to get a better insight about the functionality of the deep neural network, and how does that really helps to achieve its task. So this is the AlexNet architecture. So the objective over here is that we basically probe into the network and figure out that what each of this intermediate layer is doing, and essentially helping the neural network to say classify the objective layers. To start off with the first layer of the AlexNet, so in the previous slide you see the AlexNet. So to start off, we look into the first the convolutional filters which are present in the first layer of AlexNet. So you could see over here that there are the size of each of the filters in the first layer is 3 cross 3, and it spans across the RGB channel of the input. So it's 3 cross 11 cross 11, and we have got 64 such convolutional filters at the first layer. And the same notion follows for the other architecture, let that be ResNet 18, ResNet 101, or ResNet 121. So you could see over here that the first layer, or the filters in the first layer, essentially are trying to figure out some basic gradient or the edges that are present in the images. And this is quite evident in almost every network that you see. Moving on from the first layer to the successive layers of the deep neural network, you can see that for layer 2, which is consider a filter of size 7 cross 7, which spans through the RGB that's of the input, and there are 16 such filters at the first layer. And now this would produce 16 different output in the next layer. And now you could see the different convolutional filters in this block. The first block basically this basically shows the 16 different filters that we have in the first layer, and we have summed up the RGB channel information together. So you just get to see only 16 different filters, but each of the size of each of the filter is 7 cross 7. In the next block, you get to see the filters of size 7 cross 7, but there are 20 such filters that we get to see in this layer, because the first layer produces 16 outputs, and then we have 20 different convolutional filters in the second layer, each of size 7 cross 7, which basically produce another set of outputs. So the point over here that of this slide is that in the first layer we could see that it's making some sense, that it's trying to understand some edges, some differences in the input image. But in the later stages, we find that it's basically trying to show some abstract features, so they are not truly interpretable and not really making much sense. So, and then we get on to visualize the last layer of the neural network, which suppose for this case is that 4096 cross dimensional vector. And then what we do for this is we already did this exercise of this nearest neighbor. We just take the input image and then we compare it with all other images that we have in the database. And then in the pixel space, we try to compare the difference and find that which one of the images in the database is closest to that. So in that exercise, we could find that even for the dog, you could see that many other images which are not really having dog in it got considered to be quite close to that of the input image. But instead of going for that, if we consider the distance in the feature space, after we have extracted some meaningful information from the input image, we can find that we are really able to find that for any test images, the nearest neighbors are pretty much semantically close to what we have in the test image. So the leftmost column that you see over here, these are all the bunch of test images that we provide to this network. And then when we ask this network, and then when we just try to figure out that which one of the images in the database is close to this particular image, then we find that it's almost the flowers. And the same goes for elephants and dogs. So semantically, they convey the same information. And if you consider minute details such as the orientation of the elephant in the test image is different from few other images that it could find is close in the feature space, it's completely different. So for these two cases, you see it's completely different in comparison to that of the orientation of elephant in the test image. So now it basically shows that while we compute the distance in case in the pixel space, it doesn't really takes into account the semantic in the image, but while we try to take the difference in the feature space, it does really take into account the semantic information and finds out that which of the images are really closest to the test image. This is another way of visualizing images, that is dimensionality reduction. So the simple dimensionality reduction technique that we all possibly got introduced to is PCA, which is basically a linear transformation from the high dimensional space to the low dimensional space. But there is one more variant to it, which is known as this T-distributed stochastic neighborhood embedding, I guess. Yeah, that's the name. So that's an advanced version of PCA, which uses a nonlinear transformation from the high dimensional space to the low dimensional space. And what you see in this slide is basically the m-list digits when they are being mapped to the two-dimensional space. Means the m-list digits, each of the images of the handwritten digits are of size 28 cross 28. So that basically gives you the dimension of the feature space where the input image is, and then you basically get it mapped to the two-dimensional space. So it shows you that each of the images, they are quite unique in their own sense, and you can find that basically they form different clusters. So each of the cluster represents the different digits, the handwritten digits. And then if you just see only the black dots over here, and then it really doesn't make much sense that what exactly each of these clusters convey to you. But there is a small representation of the same in the colored form. That basically gives you that each of those clusters represents a class of digits. I don't have the slide with me, but there, if you basically apply the PCA over the m-list data set, you would find that it's only a single black blob. So you won't be able to figure out that the clustering of the images that essentially tells you that, okay, these set of images belong to a different category altogether. So this is another technique of really understanding that how we can map the high dimensional information to the low dimensional space, and that will help us to visualize things. This is another example. Over here, what we do is that we take the input images, we pass on to the network till the last layer, which gives us a 4096 dimensional feature vector, and then we map those 4096 dimensional feature vector to a two-dimensional space, and then we try and understand whether the similar images they map to the same space or the same or closely located point in the 2D space or not. So you could see that there are images which are having very strong green intensities around this region, and also some strong blue intensity around this region. But it's really hard to decipher anything out of this that what exactly it tries to convey. But the whole point of doing this exercise is to really understand that each of the images, they really have got some essential features which basically clusters them together when we try to visualize them in low-dimensional space. This is one very good visualization tool, I would say, which helps us to figure out that what each of the activation map or the feature map. So I guess you all are aware of the feature maps. So feature maps are all the intermediate information of the features that we produce in the neural network. So using this visualization technique, which is developed by Yusinski. So what he does is that he takes the AlexNet and he tries to understand that what exactly a feature map in each of the convolutional layers of the AlexNet is trying to do. For this slide, we have considered the conf5 layer and the conf5. There is some mistake in the slide. It should be 256 cross 13 cross 13. It's written 128 because you know AlexNet has got two parts of the network running in two different GPUs, so each of them has got 128. So essentially, it should be 256. And you could also figure out that the total number of blocks over here are 256 in count, 16 rows and 16 columns. And each of the cells in the blocks, each are of size 13 cross 13. Okay, so 13 cross 13 blocks essentially tells you, shows us the information about the feature map. So this slide tells us that when we present the picture of an image or picture of human face, then out of all these feature maps in the fifth convolutional layer, this particular feature map gets activated the most. So that leaves us with the information that this feature map is essentially looking for faces in the images. And moreover, if you look into the paper of Yusinski, then you will find that even this feature map of the conf5 layer gets activated with the face of a lion. So it's nowhere only restricted to finding faces in the images of human. It can also pretty well find the faces of other animals. Okay, and then we just try and understand that what each of these feature maps in the intermediate layer they are trying to do. So this is just a technique to see that to what input a feature map basically gets activated the most. So in this case also we have selected the conf5 layer and then we pick a channel that's 17 out of 128 for this particular block, and we just then try to see that for a particular feature map, what section of the input really leads to the maximum activation of that feature map. So we could see that for that 17th feature map, it's mostly the circular objects in the input, or the patches containing the circular objects or curved line that is mostly leading to the activation of that particular feature map. And you can just do this exercise for any other feature map and any layer, and then you could see that what information really leads to the activation of that feature map. So the whole idea of doing this exercise is to find out that how exactly the neural network is trying to extract meaningful feature and then leading to a conclusion or as per the task, let that be classification or object detection or whatever it is.
Here the maximal activation. So the maximum amount which.
No, so what we do in case of with the convolutional filter is that we go for an inner product with any of the input, right? So then also I missed another point is that when we do this exercise, we consider a pre-trained neural network. So this is a pre-trained AlexNet. Okay. So once we have a pre-trained AlexNet, we have the configuration of the filters, right? So what it does is that it basically tries to look for that particular information in the input. Okay, so whenever the inner product happens to be quite high, then you find that that particular feature map is having very high value. If a particular filter is looking for some specific information in the image and it's not able to find that, then you would find a very low value for that particular feature map.
I mean, here, what does the maximal activation mean? Maximum activation.
Maximum activation means it will have very high value for a particular input. Each of the feature map is responsible for extracting some meaningful information, right? So provided an input image, all of the feature maps won't be activated in the same way. Each will be activated in a unique way because each of the feature map is responsible for extracting some meaningful information, which is different from the other feature maps. Because if you remember, each of the feature map is basically generated by the convolutional filters, which does an inner product with the input and then it produces the output. So if the convolutional filter is looking for some specific features and if it doesn't find it, then it really won't have a high activation. Yeah, go ahead.
That's the two slides. Okay, sorry. Some images are pure black. Black. That means that it's after it maybe it's goes to some value and it makes those things that
Exactly. Exactly.
Sorry, can you say that again? What did he do?
So this question was that he finds that few of the blocks or few of the cells in this matrix it's completely black. So the whole idea over here is that those activation maps or the feature map didn't get any input because the filters were looking for something which was not present in the input. So that's why nothing came up with that feature map. Okay. So now let's look for some salient features which are present in the input image, which leads to the identification or classification of an image as elephant. So the exercise over here is that we take a patch and we just try to span it across the image and then try to figure out that okay, which part of the image is really leading to the classification of this image as elephant. If we just happen to block a salient region of the input image, then we will find that the classification score is quite poor. Okay. So as you could see that for the first image, when the patch was placed somewhere on the ground, so it really doesn't make much difference. So the classification score was quite high. But when we took away some meaningful information, which is quite relevant for classification of this image as elephant, then the classification score got dropped. And this is a heat map with the red color indicating the most salient regions in the image, and the yellow and white color the least significant one. So you could see that for elephant, the region around the head is quite significant. Even for the schooner, it's the same. And then for go-kart, we could see that there are some background information that's also taken into account for identification. This is pretty much dependent on the image that you use for training the network. While training the network, if the set of images that you consider has pretty much got the same background, then it essentially tells the network that okay, fine, for go-kart you need to have these type of features, and that's it. And if you have got wide variation in the input images for go-kart, then possibly these red regions wouldn't have appeared for the background. Okay. If you guys have got any question, then feel free to ask because I'm not the pro, so I might just keep on discussing stuff, but without getting to know whether you are following.
What does saliency mean here? What does saliency mean here?
So saliency basically means that what's the important or essential information that you have in the image, which leads to the proper classification of that image to any of the classes. That's a literal definition of salient, I guess. Sure. This heat map?
No, the right one.
Yeah, those heat maps, these the images in red, yellow, and white. Yeah. So what you do is that you select the patch size and then you basically span it across the entire input image, and then you could decide the stride size of your own, like how much you're going to move that patch, and that basically generates this heat map.
So here red means it's important feature.
Yeah, it's important.
Okay.
And this heat maps are for description or the class?
Could you repeat?
These heat maps
Yeah.
are for descriptors or for the whole class?
So this is for this picture. So I mean to say that this is quite unreasonable to have a very high value around this region, right? Because there is no go-kart over here. So that's what I said, that it pretty much depends on the data set that you use for training the network. if for every go card there is this similar background, then you could consider that to be essential component. Okay, so the other technique for doing this is that to apply the backpropagation information to really generate the salience information. So what we do in this technique is that given an input image, we basically try to make changes in the pixel space itself and try and understand that how the classification score affects by that. By that I mean to say that you change any of the input pixel and then you see that whether the classification score drops or not, and you repeat this for every pixel that you have in the image. So that's another way of identifying that which are the essential which are the essential features of an image which leads to this classification, and these are the results that been generated for the different classes, and it's pretty much able to figure out what is semantically essential for the network to really figure out that, okay, there is a dog in this part of the image, and there is this boat in this part of the image, or car in this part of the image. This is also an alternate technique to do segmentation of the input images to find out that what the object is. As you could see it, that by changing the different pixel intensities, we are really able to find out that how much that affects the class score. So this is also being used for segmentation of the images. And here are some results, but it's been reported in the literature that this method is not that robust enough to really produce good segmentation results. I don't know whether you guys have studied the segmentation network or not till now. Did you guys study the segmentation network? No, in the class. Okay, so possibly in the following lectures it will come up. So then we'll see that the segmentation networks are quite robust, and this is very much susceptible to the input images that we do. Okay, so getting on with another method which is known as the guided backpropagation. So the idea over here is also quite similar, that you pick a single intermediate neuron and then you basically try to compute the gradient of that neuron with respect to the pixel image, image pixel, and then figure out, generate or synthesize an image that would help you to find out that, okay, what content in the image really is leading to the activation of a particular neuron, or you would say a particular content in a feature map, right? So before I get into that, there are other methods before this guided backpropagation came into being. One is known as the deconvolutional network. How the deconvolutional network works is that, suppose consider the first image, which is basically a forward pass. So you will see for the negative values there is no value passing on to the next layer. So if we know that when no value is passing on to the next layer for a few of the nodes, then at the time of backflow of the gradient, we really don't consider those nodes, right, to pass on the information to the previous layers. I guess you did the same for your last assignment. So now, as you could see that if this is the computed gradient, so we really don't pass on the information where we have got zero values after applying the value activation. So all these indices we really don't pass on any values, and then this is the usual way the backpropagation works. Followed by that, there was another method which is known as the deconvolutional network. Though this word or terminology is not correct, we really cannot go for a deconvolutional operation. So later it was being corrected as transpose convolution. Anyway, so what it did is that instead of really considering the forward information for passing on the gradient while you were backpropagating the information to really understand that what leads to the activation of a neuron, what it does is that after it has computed the gradient, it finds out that which of the values are less than zero. Basically, it applies value activation on this particular content, which is basically the gradient cover feature map, and which tells them, okay, fine, then these informations are not really essential for you to synthesize an image, which leads to understanding that what is essential for activation of a neuron leading of the feature map. And this guided backpropagation is basically a combination of these two methods, which takes into account the usual ReLU operation that we, the usual backpropagation methodology that we follow, having ReLU activation and the deconvolutional network, what it does is that you see it is not really passing on any information whenever we have got zeros, okay, and also considering the zeros in the forward pass for ReLU. Also for those instances, also for those indices of this feature map, we really don't pass on any information back to the previous layer while we are trying to synthesize that input image. Okay, so here are the results of this guided backpropagation. You remember that in one of the earlier slides. Here we basically try to understand that these basically are the input patches that you see on the right, on the top of the right side. This basically tells us that okay, these patches are really essential for activation of a particular feature map. Okay, now we just basically are trying to regenerate the information using this guided backpropagation for those patches which really leads to activation of a neuron in a feature map. So, are you guys able to follow this?
So these are plot activations or?
So, considering any of the nodes, considering the fifth convolutional layer, you select any of the feature map, and for that feature map, you select any of the content in that feature map. So, you are just trying to understand that what information in the input image is really leading to the activation of that particular neuron. I'll just get you a minute. So now, for this case, what we are trying to do is that we have seen in a couple of slides earlier that these patches of images in the input really leads to activation of some feature map, okay, in the network. Now we are just trying to recreate or synthesize an image that really is leading to the activation of that neuron using this guided backpropagation method.
So basic idea here is that we fix the gradients and we found the picture was the previous feature map in order to make that feature biggest.
Exactly. Yeah. So we already I already said it that we consider a pre-trained network, right? So
yeah.
The idea over here is now that we want to maximize the value of a particular neuron in any of the feature map, and then we are just trying to synthesize an image which can help us do that. There is one more condition that you should keep in mind, rather constraint I would say, that is what about the input image that you start off with?
So here the weights and the bias are always fixed.
Yeah, the weight and the bias of the network is fixed because it's a pre-trained network. We are not really trying to train a network. We are trying to understand or characterize the behavior of the network. So that's why you really don't change any of the components or model parameters of the network.
So during the backpropagation, you got whatever you plotted here.
Yeah.
These are weights that you plotted.
No, these are basically the synthesized image in the pixel space. And you are trying to understand that what in the pixel space is leading to the activation of a particular neuron in the feature map.
But what is the input in like that direction?
So that's what I said. So that's a constraint. You can start off with a random image, a random noise image, or you can start with the mean image, whatever you feel like. Okay.
This the gradient, the guided backpropagation, is it a plotting? This is plotting gradient, right?
So these are not the gradient. These are the synthesized image that you generate using guided backpropagation. You're basically trying to generate an image which can lead to maximum activation of a neuron in any of the feature. That is the plan.
So here, we arbitrarily select one feature map, right? So what if we select a feature map that's closer to the end or close to that one, close to the input? So how does the result?
Exactly. So as you move deep down the network, the receptive field of the filters basically increases. By receptive field, when we move to the end, to the end. Yeah. So the receptive field of the filters basically increases.
Right.
So when the receptive field of the filters basically increases, you would find that you try to apply the guided backpropagation method, you will end up generating an image which semantically makes more sense. Right. This is something which you basically see as a part of the image, right? A curve cannot be an image. But this is for I don't know exactly which layer it is, but this is from the initial layers. But when you try to see that deep down the network, you select any of the feature map and you try to figure out that what leads to the maximization of that neuron, you will make or you will synthesize an image which has got more semantic content.
So is that right? So if we want to show information to it, so when it's tied in practice, it's better to select the layers approaching the end. The end layers.
It depends on the application task. It depends on the application task. If you are really willing to understand that what are the intermediate features which leads to a proper conclusion, then you would definitely like to probe into the intermediate layers, right?
Right.
Because at the end you only get to know that, okay, fine, if this whole content is present in the image, then it leads to the activation. But then what really makes that, leads to the activation of the neuron for that whole content, for that you need to look into the layers which are prior to that. Because that will help you to gradually figure out that what features it's trying to build up. As you could see over here, the images makes more sense. You see, you are able to see some faces, you are able to see the face of a dog and stuff like this. This is considering the neuron which is lying deep down the network. It's not very, it's towards the end of the network. So that's why the receptive field of the filter increases and you are trying to produce something. Yeah, go ahead.
So all these guided backprop images kind of like made sense to people, right? Are there any that are, like if you applied a certain filter, might it come back and look like nothing you can kind of recognize, just noise? Does that make sense?
That could only happen for the dead reviews. Because there might be some of the nodes in your network which really doesn't get activated for this particular data. So then if you start off with a random noise and you basically try to figure out what leads to the maximum activation of a particular node, since that node never really gets activated, no information is going to flow back. I guess you're following me, because we really take into consideration this output of the ReLU while we try to feed the information back to generate the image, right? So in that case, it really won't lead to synthesization of this image, which will make more sense to you.
So am I right that if I feed the resulting guided backprop images to the neural network, I will get the largest activation? So I mean, if I feed, I use the resulting guided backprop images as the input and feed it into the neural network, then I will get the largest, say, activation.
You mean to say that if you knew that a priori what leads to the maximum activation of what leads to the maximum activation of a neuron in a particular feature map? Is that what you were trying to say?
Right.
So anyway, then you are getting the maximum activation, right? You are not trying to synthesize an image then. You are already providing an input to the network which this particular neuron is looking for. So that really doesn't make much sense. You just try to generate some content which this leads to activation, which leads to maximum activation of this data. Okay. So we saw this guided backpropagation, and there is one more technique to following this, which is known as a gradient ascent. So the gradient ascent, what it does is that instead of passing on the gradient information back to the input space, it tries to address this problem as optimization problem. So what it does is that it tries to generate an image which leads to high activation value for a neuron. It basically tries to generate an image I which leads to high activation value for a neuron. And in addition to that, it adds a regularizer just to ensure that the image that you generate in the pixel space resembles something close to the natural looking images. Because if you just try to go for this gradient ascent by making changes in the pixel space, you might end up getting images which is not really interpretable, which might not really semantically convey any meaningful information to you. So these regularizers are pretty important, and if you go through the literature, you will find that a good deal of work has been done to figure out that which regularizer would be effective to generate natural looking images. Possibly we will also walk through a few in the subsequent slide. So the standard regularizer that we incorporate in always this optimization problem is L2 loss. So since we are, I would just like to recall this, remind this that the parameters of the network in this case is frozen. We are basically trying to generate an image. So by gradient descent, I mean to say that we are making changes in the input space such that it leads to the activation of a neuron, right? So suppose this SC is basically the score of the cross entropy of the softmax layer that you apply. So you select any of the class and you are basically trying to generate an image which would lead to maximization of the softmax score. Okay, so you are essentially making changes in the image space so that the class score for that particular image gets high, and at the same time you are constraining that optimization with this regularizer, that is the L2 loss. You could see that we have added a negative sign over here and a plus over here. It's just because since we are going for maximization, so maximization is a plus, right? And the negative sign basically shows that we are trying to make minimal changes in the input image so as to generate an image which leads to maximum activation or maximize the score of a class.
How do we evaluate the image that is generated by that in this case? Like, is there any cost function for that?
This is the cost function that you are trying to optimize.
Okay, this one.
Yeah. So you basically select a class of your choice, and you basically try to generate an image which leads to maximize the score of that class.
Okay, so score is our cost.
Score is basically the factor, so, and we could use any method, but for instance, softmax is being considered as the score. As you could see, SC is basically the score for class C.
How to regularize the image? Just say the normal tune?
Yeah, it's a L2 loss. There are a bunch of regularizers which has been incorporated to make images.
The same parameters, I mean the weights.
So the weights of the network are frozen,
No,
right?
I'm not here, but it's the same way to.
Yeah, exactly. Just to squash the high intensity values that you generate in an image, because the presence of a high intensity value will ruin the entire content of the image. Suppose you have got a value of say 10,000 for one of the pixels, and everyone is around 100. So then when you scale it down, it will be 0 to 255.
Better distribution.
What's that?
Better distribution.
It's not about data distribution. It's about constraining the values of the image to a particular range.
It is called salience. So the maximizer I is called saliency map.
What is that?
So is this saliency map the I?
So this case, it's not a saliency map. We are trying to generate an image. So using this method, such as we select a class called dumbbell, then we could see that, okay, this basically is the image that we could generate, which leads to the maximization of the score of dumbbell. Okay, and then followed by that, bell papers. You remember we started with a zero image. We could also start with a random noise, and this is the output that's being generated when we start with a zero image and apply this optimization technique. This image, to some extent, it's interpretable. It's telling us that, okay, fine, there are dumbbells in the images, but there are few constraints, few challenges in this solution. That is, you don't find that it's globally consistent. That there are dumbbells all around the pixel space, right? There is not a single dumbbell. It's not globally centered. It's not globally consistent or coherent or whatever you say. And at times, it's not really interpretable, because for the cups, you will find several thousand cups are overlying one over the other, so possibly the information of cup has been lost. Dermation, to some extent, it makes sense because the texture of the skin shows up in the image. Yeah, so this is the problem with this optimization technique. To address this problem, people have introduced different regularization techniques, okay, which essentially helps us to ensure that the images that we generate happens to be close to the natural image.
If you ran this multiple times, how similar would your dumbbell be to the next time you ran it?
So it will just only keep on adding dumbbells in different parts of the images.
Right. So I'm saying, like, you can kind of, like, let's say there's like 3 dumbbells, like one at the top, 2 popcorn, and one at the bottom. If you ran it again, might it have like a different kind of pattern where they're like diagonal or something like that? Or do they
No. They keep on building on what they have. So if you have already found 3 dumbbells in different parts of the input image, then it will keep on adding more dumbbells to that input image. You won't find that the previous information is lost in the process. Few more examples for this. Okay, so here are some of the additional constraints that people have tried to introduce to make the images more interpretable. That is by adding the Gaussian blur image, then by clipping the pixel values which are quite close to 0 and clipping the small gradients. Is just because small gradients and small pixel values, they really don't contribute much to really figure out what's present in the image. It's only add noise. You will find speckles all over here and there. So these are all techniques which people have adopted, and these are the results that they could get. It seems to be an improved version of what we saw earlier, but it doesn't really is able to produce something which is globally consistent, and there is globally centered image. There are flamingos all over. There is no single flamingo which you could generate in the image, but in none of the input image you will find the head of the legs of a flamingo lying on the head of the other. So considering those constraints, it really doesn't seem to be that very much reasonable. But yes, there is improvement. These are a few more examples. And
are these just like those 4 quadrants? Are they just different initializations? They just ran 4 times and then they were produced these 4 different results. Or why are there 4? I guess.
Oh, you mean to say that these are 4 different outputs? You mean to say?
Exactly. They just start with different initializations, or
I guess yeah, that's the reason. Okay, and now here we see the output for the different layers. As we know that as we go deep down the network, the receptive field of the filters increases. So the image that it generates in the pixel space is globally, it's semantically more reasonable than the one which are at the initial stages. So for layer 2, you could only see that it's able to find out some curved edges and surfaces like this, and as we move higher and higher, closer to the end layer of the network, it really is able to produce something which is more reasonable. Okay. So the other challenge of this method is that one more thing to tell you, that this method is known as activation maximization. This optimization technique is known as activation maximization. And the limitation of this activation maximization is that it doesn't really takes into account the multiple facets of a class. By that I mean to say that the images that you see in the bottom row, they all basically represents the grocery store, right? Even the one which is in above, they all represent the grocery store. But what you would end up generating by activation maximization is only image of a particular class. And that is pretty much dominated by the number of examples that you have in your data set. If you suppose say have, if your label data set has got more images pertaining to this class, this for the grocery class, if you have more images which looks quite close to this, then you will end up generating image which is close to this. So that's a problem with this activation maximization technique. So it's not really able to capture the multiple facets that might lead to the high score value for the grocery class. So there are techniques to address that. So one of the technique is that given the data set, what you do is that you basically try to apply some clustering algorithm. Suppose you consider the class grocery. You take into account all the images that you have in your input database belonging to the class grocery, and then you apply a clustering technique. After you apply the clustering technique for each of the classes, you generate a mean image. And as we have seen that this activation maximization technique could start with a 0 image or with a random image. Instead of going for a random or 0 image, you could start with the mean image of that particular cluster. So in that case, it will help you to capture the different facet which belongs to a single class. So these are all challenges. What I would say, this, as you could see, that this is pretty much dependent on the data set. So I don't know whose limitation is this. Is this a limitation of the data that we deal with, or with the network itself, which is not able to capture or generalize itself to all kinds of things? Okay. These are the examples for this method, which is the multi-facet feature visualization. This is an improvement over the previous method in a sense that the images which are generated seems to be more coherent, at least globally. You won't find multiple lampshades spread here and there around the images. You could see a centered golf cart, and then pretty much all the images, they makes more sense in comparison to what we saw in the previous slides. So they have, I guess, they have also introduced some other priors, which really helps us to constrain the generation of these input images to this globally consistent plot. Okay, and this is something where they're dealing with the fully connected layer of a network and possibly the AlexNet, and this is what they get as well. Okay, so getting into some adversarial examples. The whole idea of this adversarial example is to make small changes, the minimum changes that you could make in the input image, so that you can fool the network. So you can consider this African elephant. You would like to generate an adversarial example. The target would be to make minimal changes to this African elephant such that it gets classified as koala. So now, visually, if you see, now for these two images, there has been changes which is made to this image so that it gets classified as koala. But visually, these changes are imperceptible. So that's basically the strength of these adversarial examples. It, in a sense, exposes the limitation that you have in the network. It tells you that, okay, fine, if you make some small changes here and there in the input image, it can really lead to catastrophic effect. So consider an example for face recognition system that you have in place. So you make some small changes in your face, and then you will find that you are able to goof up the entire system. So these pretty much exposes the limitation of in the network. You could use this information to as data augmentation technique to make the network more robust to these adversarial examples. So these adversarial examples, in a sense, it helps us to generate more robust.
So these difference filters are generated, as I understand it, with knowledge of like the network itself, right? Like how, I guess the first question, two-part question, how are these difference masks created?
Are you referring to the adversarial examples or the slide before that?
I'm talking about like this different, like the gray mask right there that changes it from African elephant.
Oh, this
to
one, the difference? Oh, yeah.
How is that generated?
Oh, there are methods for that. I guess one of the very fast and quick method is FGSM, fast gradient. I don't exactly recall the name.
Right.
That's another method which can very fast generate small changes in the input image that can lead to these adversarial examples which can fool your network.
So the real question after that, which is, can you generate these difference masks without explicit knowledge of the weights and the body, like the actual, like without explicit knowledge of the model? Does that make sense?
Yeah, I got your point. So there are two kinds of adversarial attacks. One is known as the white box attack, and another is known as the black box attack.
Right.
When you go for the white box attack, then you need to have access to the parameters of the network. Okay. So then you basically use the network parameters to really estimate the changes that you need to make in the input image to be considered as an adversarial example. And in case of the black box case, you really don't have access to the network parameters. So that's a different story altogether. So what you do is that you provide some random input image to the network and you try to find out what's the output. And then you approximate the function which is doing the transformation from the input to the output. So that's an approximation. You won't be able to get to the exact function which is learned by the neural network.
But you can still do it.
Okay, so there is one more interesting work being done by Google. I guess many of you possibly have seen this deep dream, where this really results in a hallucination effect where you produce anything out of nothing. It's produced out of thin air. You start with this input image, and then you select any of the feature maps anywhere in the network. I mean to say that could be at the initial stages or deep down the network. Then you basically try to make changes to this image, which leads to the activation of that neuron. So keep this in mind that when we talk about a feature map is generated by a set of filters, right? Now a filter has already that is meant for figuring out a set of features. So when you say that I'm trying to maximize a particular neuron feature map, then what you're trying to do is that you're trying to replicate the feature which is learned by the set of filters in the input space. So you start with this input image, but the node that you are trying to maximize, they might not be responsible for looking for skies. They might be responsible for looking for something else. Okay. Then when you try to do this maximization technique on the top of it, it will lead to production of these type of contents into the in the pixel space. It's just because you really don't have any idea what this activation map or a node in an activation map is responsible for doing. And at times it might also result in something different. It all depends which activation map you select, and then you try to maximize the score of that activation map. Just a brief idea about the method. What it does is that it basically passes on the activation map information as gradient information back to the pixel space, which leads to the generation of these contents. So, and if we just keep building on this, we will end up generating more pronounced, unrealistic contents in the images. And as these are the names that they have given to each of the components that were generated, and by the curve, I don't know. These are all unrealistic terms that they have got, and then you could generate anything out of this. Okay, so this is the output that you generate when you try to maximize the content of activation map, which is in the initial layer of the network, because the initial layer is mostly meant for figuring out the edges of the curved surfaces, and so that's what you see when you try to maximize the output of a neuron in the initial stages. This is what you get, and what you saw over here is a result of activation of the neuron of a feature map belonging to a feature map deep down the network. And if you just keep on building on this, it can even result in generation of these type of images. And this is also a very high scale version. By that I mean to say that initially it started off with a low scale, low dimensional image, and then gradually when it was keeping on building the content over that input image, it eventually resulted in a huge image because it kept on growing the size of the image also in the process.
So in the second step of the why I can't understand why they want to just assign the gradient as the activation.
So that's another way. You could have done something else also. That's another way that they have adopted to see how it goes.
So why can that amplify? I just can't understand the mechanism, like to let the gradient be the activation value.
What is that?
So previously, okay, so in the previous slides, the second step, I mean the procedure that generates the picture.
Yeah.
The second step is to set the gradient as the activation.
Right.
So why can that amplify?
Why not?
Why can that amplify the picture?
Why can that amplify the picture, you mean to say?
Yeah.
See, you anyway need to pass on the gradient information. So the choice is that what information you really consider as a gradient information to pass on to the pixel space. So they consider the activation map itself as the gradient information. Suppose you consider a case where you try to maximize the class score, right? And you have got a pre-trained network. What would you do? You would basically consider the parameters that you have in the network which are pre-trained, to pass on those values that you have already learned, the filter values, down means from the last layer to the initial layer, right? Okay, that is one technique, and the technique that they have adopted is that they consider that this is the function. Suppose say the image squared is the function. So if you take the derivative of the gradient of this image squared, it essentially leads to the image itself, right? So that is another technique that they have adopted to really pass on the gradient information. You can go for the other one also. You can try with IQ and just see how it goes.
Is it similar to the deconvolutional network? Deconvolutional.
What is that?
So is it similar to deconvolutional network?
Oh no, it's not similar to deconvolution network, because deconvolution network applies a ReLU over the gradient that you have computed.
Is the sky itself is generated the picture here?
What is that?
The sky?
The sky is the input image to the network. That's where you start from, and you keep building on that. It could have been something else. You start from there and you keep building on that input image to generate all those hypothetical countries. Okay, and this is the result which is being generated using the MIT Blaze database. The same technique, you see that these are basically the different type of buildings. These are the one that we get to see in Japan or something. Okay, so the other technique is known as feature inversion. So in feature inversion, what we try to do is that we have a pre-trained network. We pass on an input image to the network, and then we get some feature information. And what we do is that we compare that feature information to a given feature vector, which is this phi 0. And this L of phi 0 is basically, the phi of x is basically the feature which is generated for the new image that we provide into the network. So the goal over here is to really reduce the difference between the feature that you generate. And then you could also add some regularizer to this, which in this case is a total radiation regularizer. So this is also another technique. And so what it does is that, consider this image. I pass this input image to the network, I generate some feature information, and then I already have the feature which is being learned by a particular activation map. I just compare these two feature information and try to minimize the difference between them. And in the initial layer, the generated images pretty much looks to be close to that of the input image, but as we move deep down the network, since the filters, they look for something abstract, so that's why we are not really able to produce something which looks quite close to that of the input image. Okay, getting into the last part of our lecture, that is this texture synthesis. So texture synthesis is given this small input block for the texture. We would like to generate an image which is pretty much been filled up with this type of information all across. So there are these techniques which are being used as on date, where they try to take into account the information from the neighboring pixels to populate the pixel, to compute the pixel intensity of any at any unknown place. But this is a very time-consuming process. So, and then they thought of, okay, why don't we try to, and moreover, for large images, it's not really able to do a convincing job. So then they thought that why don't we try to train a neural network which will help us to generate these features in a more convincing way. So then they introduced the concept of this gram matrix. So what's it is so the basic idea of this gram matrix is that what you see this block is basically activation map, right? So the size of each of the activation map is H cross W, and then you have got C such activation map as you get to see in any layer of the neural network. So what we are trying to do over here is that we are trying to figure out the co-occurrence of the textures in the different part of the images. By that we mean to say that if we have got these pebbles at different part, we are just trying to understand that the pebbles, in which other part of the input image the pebbles are present. and that would just help us to establish the repeatability or co-occurrence that we experience in the input image. And the basic objective of using this gram matrix is just to capture that. Okay, so what we do is that, so now what you could see over here is that it selects a particular index of H and W, and for that particular H and W, it takes into account all the information across the depth. Okay, so you get a vector of size C, and then you consider another location that's of H and W, and then you get to see another vector, and each of this vector it essentially tells you the presence of the texture that you are trying to reconstruct. Okay, so they are trying to understand using this gram matrix is that whether the C in blue color at a particular index of H and W is anyway close to the C vector for the different index of H and W. So since it's basically a product of these two vectors, if you really find that there is co-occurrence of the information, the product would lead to a high value in that particular index of this gram matrix. Okay. And then what we do is that we do this for all possible combinations of H and W, and we sum over all the gram matrices that we get, and we take the average of the gram matrices to generate these textures. And we will get there how we basically how we can generate the texture using this gram matrices. So then and this is also quite efficient to compute. It's just because given this, suppose you take this vector. So considering a vector of size C, you have got C into these many number of vectors, because H and W are the different spatial locations. So considering all the spatial location, you get to generate this C cross HW number of vectors, and then if you go for, you will present that as F, and it's quite easy to compute the gram matrix. It's just because if you go for a product of F and F transpose, you'll be able to generate that gram matrix. You can work it out, it's quite simple, you will exactly get what you desire. Okay, so now the idea is that you've got a pretend network, okay, and then you pass on this input, and you, for each of the layers that you have in the network, you generate this gram matrix. Okay, keep in mind the objective is to generate an image which will be having texture similar to that of this input image. So the next thing that we will do is that we start off with average or random image or a zero image, whatever you say. We pass on that image to the same network, and then we compute the gram matrix information for that particular image. Okay. So the idea over here would be to reduce the difference between the gram matrix that you compute at each of the layers. So you see, you are basically trying to reduce the gram matrix in each of the layers. And why would one do that? The basic thing is that you would like the feature that you have in each of this layer to be close to one another. So that's the idea of computing this L2 loss between the gram matrix in each of the layers. And you could also go for while you compute the entire loss. This is for a single layer, but while you compute the entire loss, you would go for a weighted average of the difference. So that's why you would see that for the complete loss, you take a weighted average of the L2 loss that you get for the pairs of this gram matrix in each of the layers. This is the result for this as the, when I provide this as the input image. This has got this texture, and then we just try to see that how close we are able to replicate the texture that we have in the input image. If we see that if we consider the output in the layers which is deep down the network, it is quite close to that of the texture that we have in the image. But for this, there is some problem, and even for this, it's just because there is not much texture present in the input image itself, so it's not able to replicate. But considering the layers which are at the initial stages, it's not really able to capture relevant information which would help it to really replicate the content in the input image. Okay, so now this work is also been extended for this style transfer. So I guess many of you are aware of this style transfer. So what it does is that it basically it does a combination of this grammar reconstruction as we have experienced in the texture synthesis, and also the feature inversion that we have seen a couple of slides back. So this feature inversion basically does the difference between the feature and the grammar reconstruction. We go for a difference between the gram matrices that we generate. So the idea would be that given a content image and a particular style image, we would like to impose this style on the content image. Okay. So to accomplish this, we would use a combination of those two losses, as we discussed earlier. We will get to see that in the next slide. And this is the effect of the style transfer on the content image. That's a result of this process. What we'll do over here is that we start with this noisy input image, okay, and we have a pre-trained network. When we pass on this noisy image through a pre-trained network, then we are able to generate features at each of the intermediate layers, right? So now we would like to compare that particular feature with the features which is generated by this content image, because that will constrain the network to produce something which is close to this content image. Okay, that would be comparing the difference between the features, and the other constraint would be that we compare the difference between the gram matrices that we have computed for each of the layers. So if you're not able to follow, I'll just get back here. Now see, this is the operation that we will try to do with the style transfer, because for the style image, because style image has got more textures into that in comparison to that of the natural looking images, which is a content image. And we will go for this feature inversion technique, which is this one for the content image, because we would like to minimize the difference between the features between this random image and this content image, with the hope that the output image will be pretty close to that of the content image. So that's the difference in the feature space, and the gram space will ensure that the style which is being imposed on this output image, presumably close to this content image, will have the style. Anyone has got a question? Yeah.
What is this network trained for? So we said that we
Yeah.
this network.
So this network is trained for the style transfer.
So for the specific style,
It could be done for a generalized one also, we will get over here. But for this instance, what we are considering is that we select a specific style and we select a specific content image on which we want to impose this style. Okay, that's the whole idea. And this is the result that we could generate using this network architecture.
yeah, but you said we have this style and content image and a noise as the input of the pre-trained.
Yeah, so what I mean to say is that you provide this noisy image to the network, right?
Yeah.
It will produce features at every intermediate layers, right? So the idea over here would be to make those features close to that of the content image. Because we pass on this content image to the same network, we will be able to generate some features. So we want the features for this random noisy image to be close to that of the content image. So this process will ensure that the output image that you generate after a few iterations is pretty much close to that of the content image. But on the top of that, we would also like to impose that we have the style that is there in this style image. To constrain that or to incorporate that into account, what we do is that we pass on the style image to the same network, but we generate additional information to that of the feature maps which is being generated. That's a gram matrix. So we use the gram matrix. We compare the gram matrix of the style image and that of the noisy image, both of these together, okay, which will ensure that you have the style imposed on this initial random noise image. And if you keep on optimizing using this loss function, you will eventually get something which is this style. You are optimizing the loss of these two components at a time. So you see after a few iterations, you get something this advantage.
Yeah, so now that we are able to transform the style with regard to images, so I'm wondering if it's possible to transform styles with regard to languages. So,
Could be.
yeah, so has any work been done with regard to
I guess it has been. I guess it has been, because people have replicated entire novels by Shakespeare. So for Harry Potter,
Does
rationale.
that involve any new techniques beyond this? Right.
Sorry, yeah. We can take this question off. I guess I really don't have a often answer. So this is basically is the process how it eventually generates a style transfer content. That is, it starts from here and then gradually evolves to somewhere over here, as we see now. Okay. So now, as you pointed out, that can't we apply different styles to the same content image? Yes, we could do that, and this is the evidence of that. You see, we have applied different style to the same content image, so that leads to style transfer, different style transfer of the same content image.
You just change the input of the.
Yeah, you just change the input of the style image, and then accordingly the network will optimize to import that style from the output image. Okay, so now there is also a game that you could play, that which one of these two loss components you are going to give, how much weightage you are going to give to each of these loss components. If you give more weightage to that of the feature inversion, which will ensure that the content image and the content image and the output image are quite close to each other, then you would get something like this. Only the image. The style component is pretty much restricted. And on the reverse, if you give more weightage to style transfer, then you will find that the content will have been lost in the output image mostly, and this is what you could eventually land up with. So yeah, so that's a choice left to the users, and we could also apply the same thing for different sizes of images, and this is a technique where we basically we take a mixed style from multiple images by taking a weighted average of the gram matrices. By this, what they mean to say is that instead of a single style, you have got a combination of style images, and you basically try to impose multiple styles on the same content image, and this is what it eventually leads to. You are not really able to decipher that to which style this particular content image has been transformed to, because it seems to be a combination of these two styles which has been applied on the content image. So yeah, these are the different variants for style transfer, and but since you basically try to optimize a single image, that you start off with this noisy image and you try to build on this noisy image so that you could generate something this as an output. So this process in itself is, every time you try to generate this, it's very time consuming, because you select a random image and then two images, one is the style, another is the content, and you basically try to incorporate these two contents over the output. So every time you do this, it's going to take a huge amount of time. Instead of that, what people have done is that they have generated a network which is capable of generating these output images. So such that if you are able to train a network for doing this task, once you train a network, you are done. You just then provide an input, a content image, and a style image. It's going to generate an output image for you. You did not do this optimization over and over again. That's the whole idea. So this is the architecture. What you do over here is that, you see, we started off with a random noise image, and we were trying to impose this content image and the style both on that output image, right? Which started off with a random noise. But now what we do is that we feed in this content image through this network, and this network is been randomly initialized. So you never know what you're going to get as y hat. It could be the same noise image that we saw here, this one. It could be that, but you never know. So what you are essentially trying to do is that you are trying to train a network which is capable of generating these images, which would be quite similar to that of the content images, and along with that, you will have the style information present in that image. I don't know, things might be quite involving for you at this stage. If you've got any question, you can ask. But I mean to say that this network, once you have trained this, you need not go for individual optimization for generating different images which will have different content image and different style, and then you start off altogether again and you build the style transfer image. Instead, you generate this network. Once this network is being trained, you simply pass on this content image, and it will be able to generate the style transfer image for you. So that's going to make the process entirely faster. Yeah, go ahead.
My question is kind of about like auditing, which you kind of talked about, so auditing how well your network is learning. With these, this is a new field, but are we supposed to be kind of employing these methods to get an idea when our network is learning well or it's not learning well? So you would start building your network, and then perhaps like this, you're getting a feed out of a style transfer. Perhaps you're getting a feed out of what your network is.
So I know I digressed a bit from what I started off with. I started off with visualizing the intermediate layer to really figure out or to probe into the network that what each of the intermediate layer is doing. But now I'm getting into some new network design architecture which will do some other task. So this has got nothing to do with understanding the network. So the part that we covered for doing that is guided propagation, saliency map, activation maximization. Those are the stuffs which really helps us to figure out that what each of the layers in the neural network is really doing. It essentially helps us to get an idea about that. And the whole thing came into place with the idea that everyone considered this to be doing magic, right? So no one really had the idea that how exactly it's working or what features are it's really looking for to get this job done. So it's primarily being motivated by that. So yeah, that's it. And for this part of the presentation, it's not really something that will help you to probe into the network and figure out what's going on and stuff like that. It's just another network which is able to do this cool stuff. So that's it. Okay, so here are the different inputs that you provide. You basically provide this style information, and then you train the network, and then provided this as input images, the one on the left side, it is able to produce these as output images. But for that, you need not get into a separate optimization problem. You have already a trained network which is capable of transforming this content image, which will have this style in the output image. And then you get to see another network which is being trained to impose this style information on the content image, and then provided this as input images, you get to see that what's the style present in the output image. Okay. So this method is also known as a fast style transfer. It's just because you just train the network once and you are done. You just only provide the content image to the network, and that produces the output for you. And then this is just one improvement that one of the network has done. That is by replacing the batch normalization with instant normalization. So the batch normalization was a component of this feed-forward network. So that was replaced in this case by the instance normalization, and it really happened to be more effective than the batch normalization. And people now are going for a combination of the styles, so such that you train a network which is capable of generating images which are having different styles. So at the time when you have already trained this network, you are willing to produce some output. What you do is that you provide a content image and you provide as parameter what is the style that you wish to apply on that input image. So then it makes life more easier that you have got a single network which is capable of imposing different styles on the same content image. So yeah, so that is also being done, and it happened to be quite effective. And then people have also done the combination of different styles when they are being applied on the same content image. So as you could see that this is the content image, and as parameter to the network, if you just apply the different styles that you want to apply on this content image, these are the output which is being generated by you. So yeah, and then as you could see over here also, this combination of the different styles on the input image. And this basically is a blending of all of these, and it basically tells you that to what extent each of these styles have an effect on the content image. Okay, so summarizing today's Here we saw the activation maximization techniques like the nearest neighbors, dimensional reductions, maximal patches, then occlusion, and then the gradient-based techniques, which are the saliency maps. The pooling image is basically the adversarial network, the adversarial examples, and feature inversion. And yes, that's pretty much it. The slide transfer. Thanks, guys. Thanks for attention. If you've got any questions.
I was teaching.
So I was doing the use assignment, and you're supposed to add a regularization term to it makes sense to add hidden layers to regularization to a right? And then you're just in like a software once more. Just take how do you apply that to matrix? Like, how are you? Are you just adding? Are you just adding a regularization term to every element?
Yeah, they provide the size of a W matrix that is, I don't know, with the regularization information, the size of the W should be enough. So then only you can go for addition of these two.
Right, because that's what basically it's just saying like you're just coming out with a yeah, you have a it's basically trying to like there's just two layers